of my lecture series, I have proved a few vector identities. Now we are left with 4 more vector identities in this present lecture. The first vector identity we are going to prove is the divergence of A cap cross B cap. The next vector identity is curl of A cap cross B cap. The third one in this present lecture is the gradient of A cap dot B cap. The last one is curl A cap. Now we prove these 4 identities in this present lecture. I proved 3 theorems in my previous lecture. Now this is theorem number 4. In theorem 4, we take 2 vector fields A cap equals A1 I cap plus A2 J cap plus A3 K cap and B cap equals B1 I cap plus B2 J cap plus B3 K cap. Now we prove the vector identity divergence of A cap cross B cap equals B cap dot curl A cap minus A cap dot curl B cap. Let's prove this identity. First of all, consider the vector fields A cap equals A1 I cap plus A2 J cap plus A3 K cap and B cap equals B1 I cap plus B2 J cap plus B3 K cap. We know very well that their cross product A cap cross B cap is given by a 3 by 3 determinant I cap, J cap, K cap on the first row, A1, A2, A3 on the second row, B1, B2, B3 on the third row. If we expand this determinant with respect to the first row, we get A2 B3 minus B3 A2 times I cap minus J cap times A1 B3 minus A3 B1 plus K cap times A1 B2 minus A2 B1. Here we suppose C1 equals the coefficient of I cap, that is C1 equals A2 B3 minus A3 B2. C2 is the coefficient of plus J cap actually. So C2 equals A3 B1 minus A1 B3. The last component C3 equals A1 B2 minus A2 B1. In general, we take the jth component in this cross product of A cap and B cap. So let us suppose that C suffix j be the jth component of this cross product A cap cross B cap. If we put j equals 1, we get C1, which is the coefficient of I cap. If we take j is equal to, we get C2, which equals the coefficient of plus j cap. If we put j equals 3, we get C3, that is nothing but the coefficient of K cap. Now we represent this coefficient Cj or the jth component of A cap cross B cap by using the Levi-Civita tensor. The representation of the jth component Cj is given by C suffix j equals summation sigma over L summation sigma over M epsilon suffix JLM A suffix L B suffix M. This is the representation of the jth component Cj by using the Levi-Civita symbol. We have to represent the divergence of A cap cross B cap. We must understand one fact that to represent the dot product of two vectors or to represent the divergence of a vector field, we have to make use of the Kronecker delta representation to represent the cross product of two vectors or to represent the curl of a vector field. We have to make use of the Levi-Civita symbol representation. Now we need to represent the divergence of the vector field A cap cross B cap. The representation of divergence of A cap cross B cap is as follows. Div of A cap cross B cap equals summation sigma over I summation sigma over j delta suffix ij dou I c suffix j. Here the indices I and j take the values 1, 2 and 3. C suffix j is the jth component of the cross product A cap cross B cap. In this representation, we have to substitute the value of C suffix j. If we substitute C suffix j here, the representation becomes div of A cap cross B cap equals summation sigma over I summation sigma over j delta suffix ij dou I summation sigma over L summation sigma over M epsilon suffix JLM AL BM. If we send dou I inside, we obtain div of A cap cross B cap equals summation sigma over I summation sigma over j delta suffix ij sigma over L sigma over M epsilon suffix JLM dou I of ALBM. In this representation, we have to observe the term dou I of ALBM. Here we have to use the product formula of the differentiation for dou I of ALBM. Then the representation takes the form divergence of A cap cross B cap equals sigma over I sigma over j delta suffix ij sigma over L sigma over M epsilon suffix JLM times BM dou IAL plus AL dou IBM. Now we can write all the summations together at one place. Then we obtain div of A cap cross B cap equals summation sigma over I summation sigma over j summation sigma over L summation sigma over M delta suffix ij epsilon suffix JLM times BM dou IAL plus AL dou IBM. Here all the indices I, J, L and M take the values 1, 2, 3. Now instead of writing 4 summations, we can use only one summation over IJLM. This simplifies the writing of the proof. It makes the proof in a crisp way. So we can write the representation of the divergence of A cap cross B cap as follows. Divergence of A cap cross B cap equals summation sigma over the 4 indices I, J, L, M, delta suffix Ij, epsilon suffix JLM times Bm dou I Al plus Al dou I Bm. Here we have to distribute the summation between the terms. So the representation takes the form divergence of A cap cross B cap equals summation sigma over IJLM delta Ij epsilon suffix JLM Bm dou Al plus sigma over IJLM epsilon JLM delta Ij Al dou Bm. We have two summations on the RHS of the expression previously. Let us do the first summation. Consider the first summation on the RHS of the previous expression, that is sigma over IJLM delta suffix Ij epsilon suffix JLM Bm dou Al. Here we contract this delta Ij. That means we expand this summation by taking j is equal to 1, j is equal to 2, j is equal to 3. After expanding sigma over j, we left with only 3 indices ILM. So our representation becomes sigma over IJLM delta Ij epsilon suffix JLM Bm dou Al equals sigma over ILM epsilon suffix ILM Bm dou Al. Observe that we have replaced j with I and we left with only 3 indices. Here the indices I, J and L take the values 1, 2, 3. Now this can be written as sigma over ILM epsilon suffix MIL Bm dou Al. Observe that I replaced epsilon suffix ILM with epsilon suffix MIL because I, L, M are in the clockwise rotation. So epsilon suffix ILM equals epsilon suffix MIL. So I replaced epsilon ILM with epsilon MIL and obtained the expression sigma suffix ILM epsilon suffix MIL Bm dou AL. Actually, this sigma over ILM represents three summations: summation over I, summation over L, and summation over M. Let us separate the summation over M and the summation over IL. Then we obtain summation over M, summation over IL, epsilon suffix MIL, BM, dou AL. Now let us separate sigma over M with BM. Then we obtain summation sigma over M, BM, summation sigma over IL, epsilon suffix MIL, dou of AL. If we observe this part sigma over IL, epsilon suffix MIL, dou AL, this representation is by using the Levi-Civita symbol, and A suffix L is there. Dou of AL is a representative from curly A cap. So this entire representation is curly A cap. So we obtain sigma over M, BM, curly A cap, mth term. Curly A cap suffix M represents the mth component of curly A cap. As a whole, the first summation becomes sigma over IJLM delta IJ epsilon suffix JLM BM dou IAL equals summation sigma over M BM curly A cap mth component. Let us suppose D suffix M equals the mth component of curly A cap. Then we get summation sigma over M, B suffix M, D suffix M. Here the index M takes the values 1, 2 and 3. If we expand this summation, we get B1 D1 plus B2 D2 plus B3 D3. This can be written as B1 I cap plus B2 J cap plus B3 K cap dotted with D1 I cap plus D2 J cap plus D3 K cap. The first part here is nothing but B cap dotted with the second part is curly A cap. So we obtain B cap dot curly A cap. So our first summation sigma over IJLM delta IJ epsilon suffix JLM BM dou IAL equals B cap dot curly A cap. I have divided the RHS of the original expression div A cap cross B cap into two parts. Previously, I selected the first summation part and I have proved that that is equal to B cap dot curly A cap. Now, let us select the second part. Sigma suffix IJLM delta IJ epsilon suffix JLM AL dou IBM. Here we take this and in proving we shift the suffixes of the Levi-Civita symbol in the anti-clockwise direction. So we obtain a minus sign. The proof is similar to the previous part. So we obtain sigma over ijlm, delta sub ij, epsilon suffix jlm, al dou ibm equals minus a cap dot curl b cap. The sum of these two parts gives the RHS. As a whole, we obtain div of a cap cross b cap equals b cap dot curl a cap minus a cap dot curl b cap. We are done. Theorem 5. In this theorem, we are going to prove another identity. In this present theorem, we take two vector fields a cap equals a1 I cap plus a2 j cap plus a3 k cap and b cap equals b1 I cap plus b2 j cap plus b3 k cap. Here we are going to prove the identity curl of a cap cross b cap equals a cap times div b cap minus b cap div a cap plus b cap dot del times a cap minus a cap dot del times b cap. Let's prove this vector identity. First consider a cap equals a1 I cap plus a2 j cap plus a3 k cap and b cap equals b1 I cap plus b2 j cap plus b3 k cap. To prove the present vector identity, first we have to find out a cap cross b cap. A cap cross b cap equals a 3 by 3 determinant whose first row is I cap, j cap, k cap, a1, a2, a3 are on the second row, b1, b2, b3 are on the third row. We know this very well. Here we have to find out curl of a cap cross b cap, which is the LHS of our present identity. If we want to represent the cross product of two vectors, we have to make use of the Levi-Civita symbolic representation. Even we want to represent curl of a vector field, we have to make use of the same Levi-Civita symbolic representation. A cap cross b cap is a vector field. So, the curl of a cap cross b cap can be represented by using Levi-Civita. Before representing, we take c suffix I to be the ith component of curl of a cap cross b cap. If you put I equals 1, C1 equals the coefficient of I cap in curl of a cap cross b cap. C2 and C3 represent the coefficients of plus j cap and k cap in the expansion of curl of a cap cross b cap. The general coefficient or component is the ith component c suffix I and it can be represented as follows. C suffix I equals summation sigma over j, summation sigma over k, epsilon suffix ijk dou j of A cap cross B cap suffix K. Here A cap cross B cap suffix K denotes the kth component in A cap cross B cap. Now let us substitute the kth component of A cap cross B cap in the representation of C suffix I. Then it becomes C suffix I equals summation sigma over I, summation sigma over j, epsilon suffix ijk, dou j, sigma over L, sigma over m, epsilon suffix klm, a suffix L, b suffix m. Here we have to send the partial derivative dou suffix j inside and we have to differentiate ALBM partially with dou j. We can also write all the summations together. So we get Ci equals sigma over j, sigma over k, sigma over L, sigma over m, epsilon suffix ijk, epsilon suffix klm, dou j of ALBM. We can also write only one sigma over all the four indices jklm to simplify the notation. We have sigma suffix jklm, epsilon suffix ijk, epsilon suffix klm, dou j of ALBM previously. We can replace epsilon suffix ijk with epsilon suffix kij because the indices I, j, k are in the cyclic clockwise orientation. So epsilon suffix ijk equals epsilon suffix kij. After replacing epsilon suffix ijk with epsilon suffix kij, the representation becomes summation sigma over jklm, epsilon suffix kij, epsilon suffix klm, dou j of ALBM. Observe the term dou j of ALBM here. We have to apply the product formula of the differentiation for this term dou j of ALBM. If we apply the product formula for dou j of ALBM, we obtain summation sigma suffix jklm, epsilon suffix kij, epsilon suffix klm, AL dou j BM plus BM dou j AL. In this representation, we have the product epsilon suffix kij times epsilon suffix klm. This is the product of two Levi-Civita symbols. We have a formula for this product. Epsilon suffix kij times epsilon suffix klm equals delta suffix il delta suffix jm minus delta suffix im delta suffix jl. This is a relationship between the Levi-Civita symbol and the Kronecker delta. If we substitute this formula in our representation, it takes the form summation sigma over jklm delta suffix il delta suffix jm minus delta im delta jl times al dou jbm plus bm dou jal. Now we have to distribute the summation and also we have to multiply all the terms. Then we get 4 terms. Now the representation becomes summation sigma over jklm delta suffix il delta suffix jm al dou j bm minus summation sigma over jklm delta suffix im delta suffix jl bm dou jal plus sigma over jklm delta suffix il delta suffix jm al dou jbm minus summation sigma over jklm delta suffix im delta suffix jl bm dou jal. Observe that in all these 4 summations we don't have the index k, so we can remove the index k under the summation. Then the representation becomes summation sigma over jlm delta suffix il delta suffix jm al dou jbm minus summation sigma over jlm delta suffix im delta suffix jl bm dou jal plus sigma over jlm delta suffix il delta suffix jm al dou jbm minus summation sigma over jlm delta suffix im delta suffix jl bm dou jal. Remember that we have 4 parts. Let us say part 1, part 2, part 3, part 4. Now we find out each part separately. After that we substitute the results here in this expression. Remember that there are 4 parts on the RHS of the previous expression. Let us select the first part among those 4 parts in our previous expression. The first part is given by summation sigma over jlm delta suffix il delta suffix jm al dou jbm. Here we contract delta suffix il. That means delta suffix il equals 1 if I is equal to L. If I not equal to L, delta il equals 0. So this Kronecker delta suffix il forces us to replace L with I. Otherwise the entire expression becomes 0. If we replace L with I, then only we can write down the expression. If we replace L with I, we lose the index L under the summation. So our part 1 becomes summation sigma over JLM delta suffix IL delta suffix JM AL dou JBM equals summation sigma over JM delta suffix JM AI dou JBM. From this expression, we can take out A suffix I. Then it becomes summation sigma over JLM delta suffix IL delta suffix JM AL dou JBM equals A suffix I sigma over JM delta suffix JM dou JBM. Observe this summation. Here we used the Kronecker delta and the term dou JBM is a representative from the divergence of B cap. So this representation equals the divergence of B cap. If we substitute div B cap there, our part 1 becomes summation sigma over JLM delta suffix IL delta suffix JM AL dou JBM equals AI divergence of B cap. This is the part 1 of our previous expression. Now let us select the part 2 of the previous expression. The part 2 is given by summation sigma over JLM delta suffix IM delta suffix JL AL dou JBM. In this expression, we contract delta suffix IM. That means delta IM equals 1 if I equals M. If I not equal to M, delta suffix IM equals 0. So we are forced to replace M with I. If we substitute I in the place of M, we lose the index M under the summation. So our part 2 takes the form summation sigma over JLM delta sub IM delta sub JL AL dou JBM equals summation sigma over JL delta sub JL AL dou JBI. Now we have to expand this summation by taking J equals 1, 2 and 3 and L equals 1, 2 and 3 because delta 11, delta 22 and delta 33 equals 1 and all the remaining Kronecker delta values are 0. This part 2 becomes summation sigma over JLM delta sub IM delta sub JL AL dou JBM equals summation sigma over JL delta sub JL AL dou JBI. After expansion, it equals dou 1 bi a1 plus dou 2 bi a2 plus dou 3 bi a3. Now, let us choose the third part. The part 3 is given by summation over JLM delta sub IL delta sub JM BM dou JAL. Here we contract delta sub IL. That means we have to replace L with I. If we don't replace L with I, the entire expression becomes 0. If we replace L with I, then our part 3 takes the shape summation sigma over JLM delta sub IL delta sub JM BM dou JAL equals summation sigma over LJ delta sub LJ AL dou JBI. Of course, we can write sigma suffix JL delta JL AL dou JBI also. Now we have to expand this summation by taking j equals 1, j equals 2, j equals 3 and L equals 1, L equals 2 and L equals 3. Then it gives us summation sigma over JLM delta sub IL delta sub JM BM dou JAL equals B1 dou 1 AI plus B2 dou 2 AI plus B3 dou 3 AI. This completes the part 3 of our previous expression. Now we have to consider the fourth part. The fourth part is given by summation sigma over JLM delta sub IM delta sub JL BM dou JAL. In this expression, again we have to contract delta IM. That means we have to replace M with I. Otherwise, the entire expression becomes 0. After replacing M with I, we lose the index M under the summation. So, after substituting M is equal to I, the part 4 becomes summation sigma over JLM delta sub IM delta sub JL BM dou JAL equals summation sigma sub JL delta JL BI dou JAL. From this, we can take out BI. After taking out BI, it becomes summation sigma over JLM delta IM delta JL BM dou JAL equals BI summation sigma over JL delta JL dou JAL. This expression is nothing but BI div A cap. This completes part 4. Up to now, we have found the parts 1, 2, 3 and 4 from our previous expression. Now we need to substitute these four parts in the ith component C suffix I of the curl of A cap cross B cap. Now the ith component Ci equals A suffix I div B cap minus of A1 dou 1 Bi plus A2 dou 2 Bi plus A3 dou 3 Bi plus B1 dou 1 Ai plus B2 dou 2 Ai plus B3 dou 3 Ai minus Bi div A cap. This is the ith component of curl of A cap cross B cap only. Actually, curl of A cap cross B cap equals C1 I cap plus C2 J cap plus C3 K cap. If we replace I cap with E1, J cap with E2 and K cap with E3, which are the unit vectors in the direction of x-axis, y-axis and z-axis respectively, then curl of A cap cross B cap equals C1 E1 plus C2 E2 plus C3 E3. That equals summation sigma over I C suffix I E suffix I. Here we need to substitute our Ci value in this expression. Our previous last expression is curl of A cap cross B cap equals summation over I C suffix I E suffix I. There we need to substitute the value of Ci and then we have to multiply it with Ei. Thereafter we have to take the summation over I. But Ci has 4 parts on its RHS. Because it's a very big expression, we split it into 4 simple parts. In the first part, we multiply the first term of the Ci with Ei and then we sum it over I. That is summation sigma over I A suffix I divergence of B cap times E suffix I. This equals div B cap times summation sigma over I Ai. Here, if we expand this, we obtain summation sigma over I Ai div B cap Ei equals div B cap times A1 E1 plus A2 E2 plus A3 E3. That is nothing but A cap div B cap. Altogether, it becomes summation sigma over I Ai div B cap Ei equals A cap div B cap. So far, we have found the first term multiplied with Ei and taken the sum over I in the Ci expression. Now, we need to take the second term from the Ci expression and we have to multiply it with Ei and then we take summation over I. So our step 2 is summation over I A1 dou 1 Bi plus A2 dou 2 Bi plus A3 dou 3 Bi times Ei, that equals summation sigma over I A1 dou 1 Bi Ei plus summation over I A2 dou 2 Bi Ei plus summation over I A3 dou 3 Bi Ei. From these summations we can take out A1, A2 and A3. Then it becomes summation sigma over I A1 dou 1 Bi plus A2 dou 2 Bi plus A3 dou 3 Bi times Ei equals A1 dou 1 sigma Bii plus A2 dou 2 sigma Bii plus A3 dou 3 sigma Bii. Here sigma Bii means B1 E1 plus B2 E2 plus B3 E3, which is nothing but B cap. Let us substitute B cap in the place of sigma Bii. Then the RHS of our present expression becomes A1 dou 1 B cap plus A2 dou 2 B cap plus A3 dou 3 B cap. Again we can take out B cap from this expression. Then it becomes A1 dou 1 plus A2 dou 2 plus A3 dou 3 times B cap. This term A1 dou 1 plus A2 dou 2 plus A3 dou 3 is nothing but the dot product between A cap and the gradient operator del. So this becomes A cap dot del times B cap. Hence our second step is summation sigma over I A1 dou 1 Bi plus A2 dou 2 Bi plus A3 dou 3 Bi times Ei is equal to A cap dot del times B cap. Now we have to take the third term from the Ci and then we have to multiply it with Ei. After that we take the summation over I. Then it becomes summation over I B1 dou 1 Ai plus B2 dou 2 Ai plus B3 dou 3 Ai times Ei, that equals B1 sigma dou 1 Ai plus B2 sigma dou 2 Ai plus B3 sigma dou 3 Ai, that equals B1 dou 1 sigma Ai plus B2 dou 2 sigma Ai plus B3 dou 3 sigma Ai. Here sigma Ai equals A1 E1 plus A2 E2 plus A3 E3. It equals A cap. So it becomes B1 dou 1 A cap plus B2 dou 2 A cap plus B3 dou 3 A cap. If we take out A cap, this becomes B1 dou 1 plus B2 dou 2 plus B3 dou 3 times A cap. The expression inside the brackets is nothing but B cap dot del. So it becomes B cap dot del times A cap. Altogether, our this expression becomes summation sigma over I b1 dou 1 ai plus b2 dou 2 ai plus b3 dou 3 ai times ei equals b cap dot del times a cap. Now let us take the fourth term of the ith component ci and then we multiply it with ei. Later we take the summation over I. Then it gives us sigma over I bi div a cap ei. From this we can take out div a cap. So we get sigma over I bi div a cap ei equals div a cap times sigma bi ei. Sigma bi ei is b1 e1 plus b2 e2 plus b3 e3, that is b cap. So we obtain summation sigma over I bi div a cap ei equals b cap div a cap. Now we have found all the four terms. Now let us substitute them in curl of a cap cross b cap. Then we obtain curl of a cap cross b cap equals summation sigma over I ci ei. After substituting all the above four parts, we obtain curl of a cap cross b cap equals a cap div b cap minus b cap div a cap plus b cap dot del times a cap minus a cap dot del b cap. We are done. Now let us take theorem number 6. In this theorem, we are going to prove another vector identity. In this theorem, as usual, a cap equals a1 I cap plus a2 j cap plus a3 k cap and b cap equals b1 I cap plus b2 j cap plus b3 k cap. These two are two vector fields. Here the vector identity which we are going to prove is the gradient of a cap dot b cap equals b cap dot del times a cap plus a cap dot del times b cap plus b cap cross curl a cap plus a cap cross curl b cap. This identity has a symmetry in it. Now let us prove this identity. First let us consider our vector fields a cap equals a1 I cap plus a2 j cap plus a3 k cap and b cap equals b1 I cap plus b2 j cap plus b3 k cap. In the LHS of our vector identity, we have to find out the gradient of a cap dot b cap. A cap is a vector field, b cap is a vector field. Their dot product a cap dot b cap is a scalar field. After that, we have to find out its gradient. Let us first find out a cap dot b cap. To represent the dot product between the vector fields a cap and b cap, we have to use the Kronecker delta representation. So A cap dot B cap equals summation sigma over j summation sigma over k delta suffix jk a suffix j b suffix k. Here the indices j and k take the values 1, 2 and 3. Instead of writing two summations, we can write down only one summation over the indices jk. It simplifies the writing of the proof. So the expression becomes as follows: a cap dot b cap equals summation sigma over jk delta suffix jk a suffix j b suffix k. Here the sigma over jk represents two sigmas, sigma over j and sigma over k. Let us put phi equals a cap dot b cap. So phi becomes phi equals summation sigma over jk delta suffix jk aj bk. But the LHS of our vector identity in the given theorem is the gradient of a cap dot b cap. That means we have to find out the gradient of phi, because we supposed that phi equals a cap dot b cap. We know that grad phi equals del phi equals dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. But for us, x equals x1, y equals x2, z equals x3. So it can also be written as dou phi by dou x1 I cap plus dou phi by dou x2 j cap plus dou phi by dou x3 k cap. Let us replace I cap with E1, j cap with E2 and k cap with E3. Then we get grad phi equals dou phi by dou x1 E1 plus dou phi by dou x2 E2 plus dou phi by dou x3 E3. This can also be written as grad phi equals dou 1 phi E1 plus dou 2 phi E2 plus dou 3 phi E3, that equals summation sigma over I dou I phi E suffix I. Now this is the representation of the left hand side of the present vector identity. But to prove this particular vector identity, we take the RHS and we show that RHS equals LHS. If we observe the given vector identity, gradient of a cap dot b cap equals b cap dot del times a cap plus a cap dot del times b cap plus b cap cross curl a cap plus a cap cross curl b cap has 4 terms on its RHS. We find each term separately and then by adding those 4 terms we find out the RHS and then we show that it is equal to the LHS. So let's find out each term among those 4 terms on the RHS separately. First, let us choose A cap cross curl B cap. Let's find out this term A cap cross curl B cap. This A cap cross curl B cap can also be written as A cap cross del cross B cap, because del cross B cap is nothing but curl B cap. So A cap cross curl B cap equals A cap cross del cross B cap. Suppose that C suffix I represents the ith component of the cross product A cap cross curl B cap. This ith component C suffix I of A cap cross del cross B cap can be represented as C suffix I equals summation sigma over j summation sigma over k epsilon suffix ijk A suffix j del cross B cap suffix k. In this notation, del cross B cap suffix k is the kth term of the curl B cap. Here, instead of writing two summations, we can write a single summation over j and k. We have to substitute the del cross B cap suffix k also here. Now C suffix I can be written as C suffix I equals summation over jk epsilon suffix ijk A suffix j del cross B cap suffix k. Let us substitute the kth term del cross B cap suffix k here. Then it becomes C suffix I equals summation sigma over jk epsilon suffix ijk A suffix j sigma over lm epsilon suffix klm dou suffix l bm. Here the indices j, k, l and m take the values 1, 2 and 3. Now let us write all the summations together. Instead of writing 4 summations for j, k, l and m, we write only one summation over these 4 indices. Now the ith component C suffix I can be written as C suffix I is equal to summation sigma over jklm epsilon suffix ijk epsilon suffix klm aj dou lbm. Here epsilon suffix ijk can be replaced with epsilon suffix kij because the indices I, j and k are in the cyclic clockwise rotation. So epsilon suffix ijk equals epsilon suffix kij. If we replace epsilon suffix ijk with epsilon suffix kij, the ith component C suffix I of A cap cross curl B cap becomes C suffix I equals summation over jklm epsilon over kij epsilon suffix klm aj dou lbm. Now in this expression we have the product of two Levi-Civita symbols. epsilon suffix kij into epsilon suffix klm. For this product, we have a formula in the properties of Levi-Civita symbol. This formula is the relationship between the Levi-Civita and the Kronecker delta. That is epsilon suffix kij epsilon suffix klm equals delta suffix il delta suffix jm minus delta suffix im delta suffix jl. If we substitute this formula connecting the Kronecker delta and the Levi-Civita, we obtain C suffix I equals summation over jklm delta suffix il delta suffix jm minus delta suffix im delta suffix jl times aj dou lbm. Now we have to multiply the terms and we need to distribute the summation. Then we obtain C suffix I equals summation sigma over jklm delta suffix il delta suffix jm aj dou lbm minus summation sigma over jklm delta suffix im delta suffix jl aj dou lbm. Throughout this expression, there is no k. The index k is not here throughout this expression. So we can remove the index k under the summation. If we do that, we obtain C suffix I equals summation over jlm delta suffix il delta suffix jm aj dou lbm minus summation sigma over jlm delta suffix im delta suffix jl aj dou lbm. In the first summation, we contract delta suffix il. That means if I is equal to L, delta suffix il equals 1. If I not equal to L, delta suffix il equals 0. So we have to replace L with I. Otherwise, the expression becomes 0. So in the first term, we replace L with I. In the next summation, we contract delta suffix im. That means we have to replace m with I in the second summation. Otherwise, the second summation entirely becomes 0. If we take m is equal to I, then only we can write the expression. If I not equal to m, delta im equals 0. So after replacing L with I in the first summation and after replacing m with I in the second summation, we obtain C suffix I equals summation sigma over jm delta suffix jm aj dou ibm minus sigma over jl delta suffix jl aj del bi. Now we expand these two summations. In the first summation, we have to expand summation over j and summation over m. In the second summation, we have to expand the summation for j and l. So we obtain c suffix I equals a1 dou b1 plus a2 dou b2 plus a3 dou b3 minus of a1 dou 1 bi plus a2 dou 2 bi plus a3 dou 3 bi. This gives us the expression for a cap cross curl b cap. But we must remember one thing, that this is only the ith component of a cap cross curl b cap. Now we have to take the second term on the RHS of the given vector identity. That is, we consider b cap cross curl a cap. We can find out this similar to the previous term a cap cross curl b cap. Just we have to interchange the terms a and b here. So similar to a cap cross curl b cap, we obtain b cap cross curl a cap equals b1 dou a1 plus b2 dou a2 plus b3 dou a3 minus b1 dou 1ai plus b2 dou 2ai plus b3 dou 3ai. Here in the previous expression a cap cross curl b cap, we got a negative term. Similarly, here also in b cap cross curl a cap, we got one negative term. We have to remember these two negative terms. Next, we have to take up the third term on the RHS of the given vector identity. So let us find out the third term of the given vector identity. That is b cap dot del times a cap. The b cap dot del is nothing but b1 dou 1 plus b2 dou 2 plus b3 dou 3. So b cap dot del times a cap equals b1 dou 1 plus b2 dou 2 plus b3 dou 3 times a cap. Similarly, a cap dot del times b cap equals a1 dou 1 plus a2 dou 2 plus a3 dou 3 times b cap. So far, we have found all the ith components of the RHS of the given vector identity. Now, let us take the RHS of the given vector identity. That is, RHS equals b cap dot del a cap plus a cap dot del b cap plus b cap cross curl a cap plus a cap cross curl b cap. In the RHS, we have b cap dot del times A cap plus A cap dot del B cap plus B cap cross curl A cap plus A cap cross curl B cap. Here, if we take the last two terms, A cap cross curl B cap and B cap cross curl A cap, we have found their ith terms C suffix I and D suffix I. So we obtain the RHS is equal to B cap dot del times A cap plus A cap dot del times B cap plus sigma over I CIEI plus sigma over I DIEI. Here in sigma CIEI we get 1 minus term. Similarly, in sigma DIEI we get one more negative term. These two negative terms cancel with the first two terms B cap dot del times A cap and A cap dot del times B cap. So, among the four terms, two terms get cancelled. We left with only two terms. Now, the RHS equals summation over I A1 doi B1 plus A2 doi B2 plus A3 doi B3 plus B1 doi A1 plus B2 doi A2 plus B3 doi A3 times EI. Here A1 doi B1 plus B1 doi A1 can be written as doi of A1 B1. Similarly, A2 doi B2 plus B2 doi A2 can be written as doi of A2 B2 and A3 doi B3 plus B3 doi A3 can be written as doi of A3 B3. If we substitute these things, we get RHS equals summation sigma over I doi of A1 B1 plus doi of A2 B2 plus doi of A3 B3 times EI. We can take out doi here. Then we get RHS equals summation sigma over I doi of A1 B1 plus A2 B2 plus A3 B3 times EI. If we observe the term in the brackets A1 B1 plus A2 B2 plus A3 B3, that can be written as A1 I cap plus A2 J cap plus A3 K cap dotted with B1 I cap plus B2 J cap plus B3 K cap. That is nothing but A cap dot B cap. So instead of that bracket, if we substitute A cap dot B cap, we obtain RHS equals summation sigma over I doi of A cap dot B cap EI. This gives us sigma over I doi phi EI, because in the beginning of the proof we supposed that phi equals A cap dot B cap. Then the RHS equals summation sigma over I doi phi EI. If we expand this summation, we get dou 1 phi E1 plus dou 2 phi E2 plus dou 3 phi E3, or it can also be written as dou 1 of a cap dot b cap e1 plus dou 2 of a cap dot b cap e2 plus dou 3 of a cap dot b cap e3. This can also be written as the gradient of a cap dot b cap that equals grad a cap dot b cap that equals the LHS. So we have proved our vector identity, that is the gradient of a cap dot b cap equals b cap dot del times a cap plus a cap dot del times b cap plus b cap cross curl a cap plus a cap cross curl b cap. So we have completed the proof of this vector identity. Our last vector identity is provided in this theorem, theorem number 7. In this theorem, we select a vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap. Here, the vector identity which we are going to prove is del cross of del cross a cap equals del of del dot a cap minus del square a cap, or it can also be written as curl of curl a cap equals grad of div a cap minus del square a cap. Let us prove this identity. Consider our given vector field a cap equals a1 I cap plus a2 j cap plus a3 k cap. We can find out its curl del cross a cap. Actually, del cross a cap is a 3/3 determinant. I cap, j cap, k cap on the first row, dou 1, dou 2, dou 3 on the second row, a1, a2, a3 on the third row. After finding curly a cap, we get one vector field, curly a cap. We have to find out curl again to this vector field, curly a cap. Then we obtain curl of curly a cap or del cross of del cross a cap. Let us suppose that C suffix I is the ith component of curl of curly a cap. So this ith component C suffix I of del cross a cap can be written as C suffix I equals summation sigma over j summation sigma over k epsilon suffix ijk dou j of del cross a cap suffix k. Here del cross a cap suffix k represents the kth term of curly a cap. Here, instead of writing two summations, we can write only one sigma over the indices jk. Then we obtain C suffix I equals summation sigma over jk epsilon suffix ijk dou j del cross a cap suffix k. Here we have to substitute the kth component del cross a cap suffix k of curly a cap. So we obtain C suffix I equals summation sigma over jk epsilon suffix ijk dou j sigma over lm epsilon suffix klm dou l of eam. If we write all the summations together, we get C suffix I equals summation sigma over jklm epsilon suffix ijk epsilon suffix klm dou j dou l am. Here, because the indices I, j and k are in the clockwise rotation, we can replace epsilon suffix ijk with epsilon suffix kij. Then we obtain Ci equals summation sigma over jklm epsilon suffix kij epsilon suffix klm dou j dou l am. Here again we have the product of two Levi-Civita symbols. So we have to use the formula epsilon suffix kij times epsilon suffix klm equals delta suffix il delta suffix jm minus delta suffix im delta suffix jl. If we substitute this formula, we obtain C suffix I equals summation over jklm delta suffix il delta suffix jl minus delta suffix im delta suffix jl times dou j dou l am. Here, throughout this expression, we don't have the index k, so we can leave the index k under the summation. So we obtain Ci equals summation sigma over jlm delta il delta jm minus delta im delta jl times dou j dou l am. Now we multiply all the terms here. Then we obtain Ci equals summation sigma over jlm delta suffix il delta suffix jm dou j dou l am minus summation sigma over jlm delta suffix im delta suffix jl dou j dou l am. The ith component Ci of curl a cap can be written as C suffix I equals summation over jlm delta suffix il delta suffix jm dou j dou l am minus summation sigma over jlm delta suffix im delta suffix jl dou j dou l am. As usual, we replace L with I in the first summation and we replace M with I in the second summation. Then we obtain Ci equals summation over Jm delta suffix jm dou j dou am minus summation over jl delta suffix jl dou j dou l ai. From the first summation we can take out dou I and we expand the second summation over j and over l. Then we obtain Ci equals dou I of summation sigma over jm delta suffix jm dou j am minus dou 1 square ai plus dou 2 square ai plus dou 3 square ai. Here in the first term the summation is summation sigma over jm delta suffix jm dou jam. This represents the divergence of a cap. If we substitute div a cap, there we obtain Ci equals dou I of div a cap minus of dou 1 square ai plus dou 2 square ai plus dou 3 square ai. Now curl of curly a cap equals del cross of del cross a cap equals C1 I cap plus C2 j cap plus C3 j cap. Here C1 comma C2 and C3 are components of curl a cap. This can also be written as curl a cap equals del cross of del a cross a cap equals C1 E1 plus C2 E2 plus C3 E3, which equals summation over I Ci Ei. Here we need to substitute the value of Ci. Then we obtain curl of curly a cap equals del cross of del cross a cap equals summation sigma over I dou I of div a cap minus of dou 1 square ai plus dou 2 square ai plus dou 3 square ai times ei, which equals summation sigma over I dou I of div a cap times ei minus sigma over I dou 1 square ai plus dou 2 square ai plus dou 3 square ai times ei. The first summation is nothing but the gradient of div a cap. The second summation is nothing but the Laplace operator applied on a cap. So we obtain curl of curly a cap equals gradient of div a cap minus del square a cap. This can also be written as del cross of del cross a cap equals del of del dot a cap minus del square a cap. This proves our last identity. I proved 3 vector identities in part 7 of my lecture series on vector differentiation. In this present lecture, I have proved 4 vector identities. Actually, all the vector identities follow some symmetry. So, it is very easy to remember all the vector identities. Now, practice all the vector identities and the representations by using Kronecker delta and Levi-Civita tensor. If you have any queries, please contact me through email. Thanks for listening.